The universe is a graveyard. We're surrounded by dead planets, billions of them. For every living world, there might be a billion corpses, planets that froze, boiled, suffocated, or were flayed alive by their own stars. Earth could have easily been one of them. Is Earth really the exception, or are we next? And here is a question. If you could teleport anywhere in the universe, where would you explore first? Let me know in the comments. I will pin the most creative answer. Now let's begin. Imagine being the first humans to actually see the surface of another world circling a distant star, not just detecting its presence through wobbles in starlight or dips in brightness, but truly observing what that planet looks like. That's exactly what astronomers accomplished in 2026 when they pointed the James Webb Space Telescope at a rocky planet called LHS 3b. This world sits 49 light-years away from Earth. To put that in perspective, if you could travel at the speed of light, crossing the entire distance our planet travels around the Sun in just 8 minutes, it would still take you 49 years to reach this exoplanet. It's not exactly next door, but in cosmic terms, it's practically in our backyard. What did we find when we looked at this world? The lead scientist on the study, Laura Kreidberg, didn't mince words. She called it a hellish, barren rock. Picture Mercury, our solar system's innermost planet, with its cratered, radiation-blasted surface. Now make it even more extreme. That's LHS 3844b. The planet has no atmosphere, none whatsoever. When scientists analyzed the infrared light coming from its day side, they found temperatures soaring to around 782 degrees Kelvin. That's roughly 968 degrees Fahrenheit, hot enough to melt lead. But here's the truly fascinating part. The night side is likely freezing cold, plunging to temperatures near absolute zero. Why such an extreme difference? Because without an atmosphere, there's nothing to distribute heat around the planet. On Earth, our atmosphere and oceans act like a giant climate control system, moving warmth from the equator to the poles from day to night. But on LHS 3844b, one side perpetually faces its star, baking in endless radiation. The other side faces the eternal darkness of space, frozen solid. The surface itself appears to be covered in something called regolith. That's the scientific term for loose, fragmented rocky material that accumulates over eons of bombardment by micrometeorites and intense stellar radiation. Think of it as cosmic dust and rubble that's been piling up for billions of years. The surface is dark, ancient, and utterly lifeless. This isn't some rare exception either. Another planet studied by the James Webb Space Telescope, GJ3929b, tells a similar story. Observations from late 2025 revealed this terrestrial world also lacks any significant atmosphere. Scientists measured its dayside temperature at 782 degrees Kelvin, almost identical to LHS 3844b. What makes this discovery particularly striking is that these observations ruled out the presence of carbon dioxide atmospheres thicker than 100 millibars. For reference, Earth's atmospheric pressure at sea level is about 1,000 millibars. So we're talking about atmospheres that would be 10 times thinner than Earth's at minimum. And even those couldn't exist on these worlds. Why does this matter? Because carbon dioxide is often considered a last resort atmospheric gas. It's heavier than hydrogen or water vapor, harder to strip away, and common throughout the cosmos. If a planet can't even hold on to carbon dioxide, it means something catastrophic has happened to its atmosphere, or perhaps it never had one to begin with. Now let me take you to another planetary system that's captured the imagination of astronomers and the public alike. It's called TRAPPIST-1, located about 40 light-years from Earth. This system is remarkable because it contains 7 Earth-sized planets, all orbiting a small, cool red dwarf star. When it was first discovered back in 2017, excitement rippled through the scientific community. Three of these planets, designated E, F, and G, orbit within what we call the habitable zone, the region where liquid water could theoretically exist on a planet's surface. For years, many of us wondered if these worlds might harbor life. But in 2025, the James Webb Space Telescope delivered disappointing news. Thermal observations of TRAPPIST-1b and c revealed that these inner planets have no thick atmospheres either. They're likely bare rocks, much like the other dead worlds we've been discussing. If you're finding this journey through the cosmos fascinating, please give this video a like. It genuinely helps me continue bringing you these stories from the frontier of space exploration. So what's happening to all these planets? Why are so many of them stripped bare, devoid of the protective atmospheric blankets that make worlds like Earth habitable? The answer lies in the nature of their host stars. Many of these exoplanets orbit red dwarf stars, the most common type of star in our galaxy. Red dwarfs are smaller and cooler than our Sun, which means a planet has to orbit much closer to receive enough warmth for liquid water to exist. But here's the problem. Young red dwarfs are incredibly violent. They unleash powerful flares and intense ultraviolet radiation that can strip away planetary atmospheres in a process called atmospheric erosion. Think of it like this. Imagine you're trying to hold on to a handful of sand while standing in a hurricane. The wind just rips it away from your grasp, grain by grain. That's essentially what's happening to these planets. The charged particles and radiation from their stars are literally tearing away the gases that could have formed protective atmospheres. But stellar radiation isn't the only culprit. There's another process at work, one that's equally devastating. It's called hydrodynamic escape, and it happens when a planet's upper atmosphere gets so hot from stellar radiation that gas molecules literally achieve escape velocity and fly off into space. Here's how it works. When ultraviolet light from a star hits the upper layers of a planetary atmosphere, it heats those gas molecules to extreme temperatures. If the planet's gravity isn't strong enough to hold on to those superheated molecules, they just keep accelerating upward until they break free entirely. Over millions of years, this process can completely strip a planet of its atmosphere, leaving behind nothing but bare rock. Earth experiences a tiny amount of this process, but our planet's stronger gravity and protective magnetic field keep it in check. We lose only a few kilograms of atmospheric gas per day, which is basically nothing compared to our atmosphere's total mass. But smaller planets orbiting close to active stars, they can lose entire oceans worth of material. Speaking of oceans, let's talk about water. Scientists used to believe that many rocky exoplanets might be water worlds completely covered in deep oceans with possibly thick atmospheres of water vapor. It was an appealing idea, one that suggested abundant opportunities for life throughout the galaxy. But recent research is forcing us to reconsider. A study presented at the European Geosciences Union General Assembly in Vienna during 2026 delivered some startling preliminary findings. According to this research, hellish Venus-like planets may be approximately twice as common as habitable planets that formed with oceans. Let that sink in for a moment. For every world that might resemble Earth, there could be two that resemble the inferno of Venus. Venus, our neighboring planet, is often called Earth's evil twin. It's similar in size and mass to our world, but the resemblance ends there. Its surface temperature reaches about 864 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure at the surface is 92 times greater than Earth's, equivalent to being nearly a kilometer underwater in our oceans. And the atmosphere itself is composed primarily of carbon dioxide, with clouds of sulfuric acid floating through the sky. How did Venus end up this way? Scientists believe it experienced something called a runaway greenhouse effect. Early in its history, Venus may have had liquid water on its surface, but as the young sun grew brighter, temperatures rose. Water began evaporating into the atmosphere. Since water vapor is itself a greenhouse gas, This trapped even more heat, causing more evaporation, which trapped more heat in an unstoppable feedback loop. Eventually, all of Venus's water evaporated. Ultraviolet radiation from the sun broke apart the water molecules in the upper atmosphere. The lightweight hydrogen escaped to space while the oxygen reacted with rocks on the surface. What remained was a thick blanket of carbon dioxide, creating the pressure cooker world we observe today. Now imagine this scenario playing out across the galaxy, on world after world. That's what the research suggests might be happening. When rocky planets form, they go through a phase where their surfaces are molten oceans of magma, heated by the energy of formation and radioactive decay. During this magma ocean phase, gases trapped in the molten rock bubble up to the surface, creating a primordial atmosphere. Sean Jordan, a postdoctoral fellow at ETH Zurich, who led the study, explained that it's remarkably easy for planets to form carbon dioxide-dominated atmospheres straight from their magma ocean phase. The chemistry favors it. Carbon dioxide is stable, abundant, and readily released from molten rock. So many rocky planets probably start their lives shrouded in thick carbon dioxide atmospheres. But here's where things get interesting and a bit disturbing. If these planets orbit too close to their stars, or if their stars are too active, that carbon dioxide atmosphere can trigger a runaway greenhouse effect just like on Venus. The planet heats up, potentially losing any water it might have had. Even if it doesn't go full Venus, the intense stellar radiation can gradually strip away the atmosphere over billions of years, leaving behind the bare, lifeless rocks we're now discovering. This brings us to a crucial question about planetary habitability. We've spent decades searching for planets in the habitable zone, sometimes called the Goldilocks zone. Not too hot, not too cold, but just right for liquid water. But we're learning that being in the habitable zone is necessary, but not sufficient for a world to actually be habitable. You can have a planet at exactly the right distance from its star, but if it doesn't have enough mass to hold on to an atmosphere, it won't matter. If the star is too active and strips away the atmosphere, it won't matter. If the planet doesn't have a magnetic field to deflect charged particles, it won't matter. If it goes through a runaway greenhouse phase early in its history, it won't matter. Habitability, we're discovering, is incredibly fragile. It requires a perfect storm of conditions all coming together and staying together for billions of years. This realization connects to something I discussed in another video about the immense challenges we'd face trying to travel between the stars. If you want to understand more about why interstellar travel might remain forever beyond our reach, check the video on the card above. The real reason we will never travel among the stars. It explores the brutal physics that makes crossing the vast gulfs between solar systems so incredibly difficult, even for advanced civilizations. But let's return to our dead worlds and explore another fascinating discovery. Remember how I mentioned that many exoplanets orbit red dwarf stars? Well, there's something particularly challenging about these stellar neighbors. Red dwarfs can remain active, spewing radiation and flares for billions of years longer than Sun-like stars. Our Sun, a G-type yellow dwarf, had a violent youth, but it settled down relatively quickly in cosmic terms. Within a few 100 million years, it had calmed to the stable, steady star we know today. This gave Earth's early atmosphere and oceans time to develop and stabilize before life emerged. Red dwarfs, on the other hand, can remain volatile for 10 billion years or more. Some may never fully settle down. Imagine trying to nurture life on a planet while its star regularly unleashes flares that irradiate the surface with deadly radiation. It's like trying to grow a garden during an endless series of nuclear explosions. Yet red dwarfs make up roughly 70 to 75% of all stars in the Milky Way galaxy. If planets around red dwarfs struggle to maintain habitable conditions, that immediately eliminates 3/4 of all possible stellar systems from consideration. The implications are staggering. there's also the matter of tidal locking. When a planet orbits very close to its star, as many red dwarf planets do to stay warm enough, gravitational forces can lock the planet into synchronous rotation. One side perpetually faces the star, the other perpetually faces away, just like how one side of our moon always faces Earth. This tidal locking creates extreme temperature gradients. The day side bakes under eternal sunlight, while the night side freezes in perpetual darkness. If the planet has an atmosphere, winds might circulate heat between the two hemispheres, creating a narrow, habitable band around the terminator, the line between day and night. But if atmospheric erosion has stripped away those gases, you're left with the scenario we observed on LHS 3844b, one hemisphere scorching hot, the other frozen solid, and nothing in between. Now you might be thinking, surely not every planet meets this fate. What about planets around sun-like stars? What about worlds that formed farther out and migrated inward later? What about planets with strong magnetic fields that can deflect stellar radiation? You're absolutely right to ask these questions. The universe is vast and diverse, and not every world follows the same path. But here's what the data is increasingly showing us. Habitable worlds might be far rarer than we hoped. Let's examine another intriguing case. In March of 2026, scientists published research about a planet called L98-59d. This super-Earth orbits a red dwarf star about 35 light-years from our solar system. Using the James Webb Space Telescope, researchers discovered something unexpected. This planet appears to have a permanent magma ocean on its surface. Think about that for a moment. A world where the entire surface remains molten, churning oceans of liquid rock heated to thousands of degrees. It sounds like something from a science fiction nightmare, but it's real. The planet is tidally locked to its star, and the intense radiation keeps the day side in a perpetual state of molten fury. But here's where it gets truly fascinating from a scientific perspective. That magma ocean is interacting with the atmosphere above it. Gases dissolved in the molten rock are continuously bubbling up to the surface, replenishing the atmosphere, even as stellar radiation tries to strip it away. Scientists detected signs of sulfur dioxide being produced through photochemical reactions in a hydrogen-rich atmosphere. This tells us something profound. The atmosphere isn't left over from the planet's formation. It's being actively sustained by ongoing volcanic outgassing from the magma ocean below. It's a dynamic system, a planet that's essentially one giant volcano, continuously recycling material between its interior and its atmosphere. L98-59d will likely remain in this state for billions of years. Its interior is so hot, its star so close, that the magma ocean may never solidify. This planet will never develop a solid crust, never have continents or ocean basins, never provide stable surfaces where complex chemistry could unfold. It's a world locked in an eternal infancy, unable to mature into something that could support life as we understand it. This discovery reveals yet another pathway to creating dead worlds. Even if a planet manages to hold on to an atmosphere, if it's too close to its star, it might remain in a permanent magma ocean state. No solid surface means no place for water to pool, no stable environments for prebiotic chemistry, no opportunity for life to gain a foothold. Now let's broaden our perspective and consider what all these discoveries mean for the bigger picture. When we look out at the galaxy, we see hundreds of billions of stars. Astronomers estimate there are more planets than stars, meaning the Milky Way likely contains trillions of worlds. With numbers that enormous, even if habitable planets are rare, there should still be many of them, right? Maybe. But let's do some math. If 75% of stars are red dwarfs and planets around red dwarfs face extreme challenges maintaining atmospheres and habitable conditions, we can already eliminate a huge fraction of potential homes for life. Of the remaining 25% of stars, Many are either too massive, burning too hot, and dying too quickly for life to evolve, or they're binary systems where planetary orbits might be unstable. Let's be generous and say 10% of stars in the galaxy are potentially good candidates for hosting habitable planets. That's still about 20 billion stars. If each has an average of one planet in the habitable zone, that's 20 billion potentially habitable worlds. Sounds promising, but now factor in atmospheric loss. How many of those planets are massive enough to hold on to their atmospheres over billions of years? How many have magnetic fields strong enough to deflect stellar wind? How many avoided runaway greenhouse effects during their formation? How many didn't experience catastrophic asteroid impacts that stripped away their atmospheres? With each additional filter, that number drops. Maybe it goes down to 1 billion, then 100 million, then 10 million. The galaxy is enormous, but the requirements for long-term habitability are stringent. There's another sobering consideration. Even if a planet manages to maintain habitable conditions for billions of years, that doesn't mean life will arise. We still don't fully understand how life began on Earth. We know it happened relatively quickly in geological terms, appearing in the fossil record within a few 100 million years after the planet's surface cooled enough to support liquid water. But we don't know if this was incredibly lucky or essentially inevitable given the right conditions. The origin of life remains one of the deepest mysteries in science. We can create some of the building blocks of life in laboratory experiments, synthesizing amino acids and nucleotide bases from simple chemicals, but going from those building blocks to actual self-replicating organisms is a leap we haven't replicated. We don't know how likely or unlikely that step is. If the origin of life is extremely improbable, requiring a series of unlikely chemical events to occur in just the right sequence, then even planets with perfect habitable conditions might remain sterile. The universe could be filled with beautiful blue worlds with sparkling oceans and nitrogen-oxygen atmospheres where nothing lives. Perfect stages with no actors. This possibility is deeply unsettling. It challenges our assumption that life is a natural consequence of habitable conditions. It forces us to confront the possibility that Earth might be genuinely unusual, not just in maintaining habitability, but in making the jump from chemistry to biology. But let's not get too pessimistic. Let's assume life does arise relatively easily when conditions are right. Even then, there's another filter to consider: the transition from simple microbial life to complex multicellular organisms. On Earth, life remained exclusively single-celled for roughly 3 billion years. That's 3/4 of our planet's entire history. Simple bacteria and archaea dominated the world, living in the oceans, forming stromatolites, gradually oxygenating the atmosphere through photosynthesis. But they never became more complex. Then, around 600 million years ago, something changed. Multicellular organisms appeared and rapidly diversified in what we call the Cambrian explosion. Within a relatively short period, geologically speaking, Earth went from a world of microbes to a world teeming with complex animals. We still debate what triggered this transition. Was it rising oxygen levels? Was it the evolution of predation creating selective pressure for larger, more complex bodies? Was it a series of global glaciation events that disrupted stable ecosystems? We're not entirely sure. What we do know is that this transition took billions of years on Earth. If that's typical, then even planets that successfully develop microbial life might remain stuck at that stage indefinitely. The galaxy could be filled with worlds where bacterial mats are the pinnacle of biological achievement. And here's another wrinkle to consider. Even complex life doesn't guarantee intelligence. Earth has hosted complex multicellular organisms for 600 million years, but intelligence on the level of humans appeared only in the last few 100,000 years. For most of Earth's history, even after complex life evolved, nothing on this planet could contemplate the stars, build telescopes, or send radio signals into space. Dinosaurs ruled Earth for roughly 165 million years. They were incredibly successful, diverse, and some species were quite intelligent by animal standards, but they never developed technology or civilization. If that asteroid hadn't struck 66 million years ago, dinosaurs might still dominate the planet today, and intelligence like ours might never have evolved. This suggests that intelligence is not an inevitable outcome of evolution. It's one possible strategy among many, and for most of Earth's history, it wasn't particularly favored. Being smart is metabolically expensive. The human brain consumes about 20% of our body's energy, despite representing only 2% of our mass. For most organisms throughout history, that investment hasn't been worth it. So even if the galaxy contains millions of planets with complex ecosystems filled with fascinating alien creatures swimming in alien oceans and flying through alien skies, most of them might lack anything we'd recognize as technological civilization. Beautiful, thriving worlds, but silent. No radio signals, no cities, no spacecraft. Now let's return to the dead worlds and explore another mechanism that can render planets lifeless: catastrophic impacts. We've talked about atmospheric erosion from stellar radiation, tidal locking, and runaway greenhouse effects. But sometimes death comes from space itself. In the early history of any solar system, the environment is chaotic. Countless asteroids, comets, and planetesimals orbit the young star, occasionally colliding with each other and with newly formed planets. These impacts can be absolutely devastating. On Earth, we've experienced major impacts throughout our history. The one that killed the dinosaurs released energy equivalent to roughly 10 billion Hiroshima bombs. It created a crater over 100 miles wide, triggered global wildfires, and threw so much debris into the atmosphere that sunlight was blocked for months or years. It was an extinction-level event that eliminated 3/4 of all species on the planet. But Earth survived because we had a thick atmosphere, oceans, and a molten interior that keeps our planet geologically active, allowing it to recover and recycle materials over time. Not all worlds are so fortunate. A sufficiently massive impact can actually blast away a significant portion of a planet's atmosphere. Imagine an asteroid the size of a mountain slamming into a planet at tens of thousands of miles per hour. The explosion doesn't just create a crater, it launches a plume of atmospheric gases into space at escape velocity. If the planet is small and the impact is large enough, this can strip away substantial amounts of the atmosphere in a single catastrophic event. Mars likely experienced this. Evidence suggests that ancient Mars once had a thicker atmosphere and liquid water on its surface. Rivers carved channels through the landscape. Lakes filled impact craters. It might have been habitable. But Mars is smaller than Earth, with weaker gravity. It also lacks a global magnetic field, which means the solar wind can directly interact with its upper atmosphere. Over billions of years, a combination of solar wind stripping and possibly major impacts reduced Mars's atmosphere to the thin wisp we see today. The surface pressure is less than 1% of Earth's. Water can no longer exist in liquid form on the surface. It either freezes or immediately evaporates. Mars became a dead world, its potentially habitable conditions lost to time. This scenario could be common throughout the galaxy. Young planetary systems are violent places filled with debris left over from formation. Planets in their early years get pummeled by impacts. Most will survive, but some might lose their atmospheres, their water, their chance at life, all because they happen to be in the wrong place at the wrong time. There's also the question of planetary mass. We've mentioned this before, but it's worth diving deeper. To hold on to an atmosphere over billions of years, a planet needs sufficient gravity. Too small and atmospheric gases, especially lighter ones like hydrogen and helium, will gradually escape to space even without stellar radiation or impacts accelerating the process. Earth is right on the edge of being able to hold on to hydrogen. Our planet's gravity can retain heavier gases like nitrogen, oxygen, and carbon dioxide, but hydrogen escapes relatively easily. That's why our atmosphere today contains almost no free hydrogen, despite hydrogen being the most abundant element in the universe. Now imagine a planet smaller than Earth, say about the size of Mars. It has even weaker gravity, making it harder to hold on to even heavier gases like carbon dioxide and nitrogen. Over geological timescales, these gases leak away. The atmosphere thins. Surface conditions become increasingly hostile to life. This is why size matters for habitability. You need enough mass to generate sufficient gravity to retain an atmosphere, but not so much mass that you become a mini Neptune, a world dominated by thick layers of hydrogen and helium with no solid surface at all. There's a sweet spot, and it appears to be fairly narrow. Recent estimates suggest that planets need to be at least 80% of Earth's mass to reliably hold on to substantial atmospheres over billions of years. That immediately eliminates many rocky exoplanets from consideration. We've discovered thousands of exoplanets, but a significant fraction are either too small to maintain atmospheres or too large, having accumulated massive gas envelopes that prevent the existence of solid surfaces. Let's talk about another category of potentially dead worlds, planets that formed in the wrong part of their solar systems and migrated inward. Planetary migration is a common process. When planets form in the disk of gas and dust surrounding a young star, gravitational interactions can cause them to spiral inward or outward from their original positions. Hot Jupiters are the classic example. These are gas giant planets, similar in size to Jupiter or larger, that orbit extremely close to their stars, completing full orbits in just a few days. Jupiter itself takes nearly 12 Earth years to complete one orbit. These hot Jupiters couldn't have formed where we find them. It's too hot close to the star for gas giants to assemble. They must have formed farther out and then migrated inward. But as these giants migrated, they likely disrupted the orbits of any rocky planets in their path. Imagine Jupiter spiraling through the inner solar system, its massive gravity throwing Earth, Venus, and Mars into chaotic orbits. Some planets might get ejected from the solar system entirely, flung into interstellar space. Others might crash into the star or into other planets. A few might survive, but in drastically altered orbits that make them uninhabitable. This means that many solar systems that might have had potentially habitable rocky planets lost them during migration events. The habitable zones around these stars might now be empty, swept clean by giant planets that passed through billions of years ago. Interstellar space itself might be filled with rogue planets, worlds that were ejected from their solar systems and now drift alone through the darkness between stars. Without a sun to warm them, these planets would be frozen, their surfaces coated in ice, their atmospheres collapsed into frozen layers on the ground. They're dead worlds in the most literal sense, corpses of planets that once orbited stars. Astronomers estimate there might be billions of rogue planets in our galaxy, possibly outnumbering planets that orbit stars. They're incredibly difficult to detect because they emit almost no light and don't pass in front of stars from our perspective. But occasionally, when a rogue planet passes between us and a distant star, its gravity can bend and magnify the starlight in an effect called gravitational microlensing. These rare events have allowed us to detect a handful of rogue planets and estimate how common they might be. Each one represents a catastrophic disruption in some distant solar system, a planet torn from its home and cast into eternal night. Now let's consider another threat to planetary habitability that's less dramatic but equally devastating over long timescales: the evolution of the host star itself. Stars are not static. They change over billions of years, and those changes can render previously habitable planets completely sterile. Our Sun, for instance, has been gradually growing brighter throughout its lifetime. When the Sun first ignited fusion in its core about 4.6 billion years ago, it was roughly 30% dimmer than it is today. This is called the faint young sun paradox, because with a dimmer sun, Earth should have been frozen solid in its early history. Yet we have evidence of liquid water on Earth going back nearly 4 billion years. Scientists think Earth avoided freezing because our early atmosphere contained much higher levels of greenhouse gases, particularly carbon dioxide and possibly methane, which trapped enough heat to keep water liquid despite the dimmer sun. As the Sun gradually brightened over billions of years, geological processes removed carbon dioxide from the atmosphere, balancing out the increasing solar radiation and keeping Earth's temperature relatively stable. But this balancing act won't last forever. The Sun will continue brightening as it ages. In about 1 billion years, it will be roughly 10% brighter than today. That might not sound like much, but it will be enough to trigger a runaway greenhouse effect on Earth. Our oceans will begin evaporating. Water vapor in the atmosphere will trap more heat, causing more evaporation, in the same deadly feedback loop that consumed Venus billions of years ago. Eventually, Earth's oceans will boil away completely. The water vapor will be broken apart by ultraviolet radiation in the upper atmosphere. Hydrogen will escape to space. Our planet will become a scorched, lifeless desert, much like Venus is today. Life on Earth has perhaps 1 billion years remaining before the Sun's evolution makes our planet uninhabitable. Now, 1 billion years is an enormously long time by human standards. Our species has existed for only about 300,000 years. Civilization has existed for roughly 10,000 years. 1 billion years is so far in the future that it's difficult to even contemplate. But from a cosmic perspective, it's a reminder that habitability is temporary. Every planet in the habitable zone of a sun-like star will eventually become uninhabitable as that star ages and brightens. The habitable zone itself moves outward over time. Planets that are comfortably habitable today will become too hot in the future. Planets that are currently too cold might become habitable, but only temporarily before they too become overheated. For red dwarf stars, the situation is different but equally challenging. Red dwarfs burn their fuel so slowly that they can remain stable for tens or even hundreds of billions of years. The universe itself is only about 13.8 billion years old, so no red dwarf has yet reached old age. They'll outlive the Sun by a factor of 10 or more. This longevity might seem like an advantage for habitability. If a planet around a red dwarf manages to survive the star's violent youth and maintain habitable conditions, it could potentially remain that way for an incredibly long time. The star won't evolve and brighten significantly for tens of billions of years, but remember those challenges we discussed earlier. Red dwarfs tend to be very active, especially when young. They produce powerful flares that can temporarily increase their brightness by 50% or more. These flares bombard nearby planets with intense ultraviolet radiation and charged particles. A planet in the habitable zone around a red dwarf might experience the equivalent of a nuclear war every few days or weeks as stellar flares scour its atmosphere. Some planets might be able to withstand this. If they have strong magnetic fields and thick atmospheres, they might weather the storm. But many won't. The flares will gradually strip away their atmospheres molecule by molecule year after year until nothing remains but bare rock. Even if a planet survives the flares, there's the issue of tidal locking that we touched on earlier. Because habitable zone planets around red dwarfs orbit so close to their stars, tidal forces from the star's gravity will gradually slow the planet's rotation until it becomes tidally locked, with one hemisphere always facing the star and the other always facing away. This creates extreme climate challenges. The day side could become too hot, while the night side freezes. Atmospheric circulation might help distribute heat, creating a habitable twilight zone around the terminator, but it's a precarious balance. If the atmosphere is too thin, it won't circulate enough heat. If it's too thick, the greenhouse effect on the day side might make temperatures unbearable. Some scientists have proposed that tidally locked planets might actually have a stability advantage. Without a day-night cycle, temperatures wouldn't fluctuate. Life could adapt to the stable conditions in the twilight zone, but we simply don't know if this would work. We have no examples to study. Every potentially habitable planet we've examined so far appears to lack the thick atmosphere necessary to make this scenario viable. Let me share another sobering discovery that reshapes our understanding of planetary atmospheres. Remember K2-18b, the planet that generated enormous excitement in 2023, when some scientists suggested it might be a Hycean world, a planet with a hydrogen-rich atmosphere overlying a liquid water ocean? More recent analysis published in 2024 threw cold water on that hope. Researchers using detailed photochemical models found that the observations of methane and carbon dioxide in K2-18b's atmosphere are actually more consistent with it being a gas-rich mini-Neptune with no habitable surface whatsoever. The methane isn't being produced by life in an ocean below, as some hoped. Instead, it's being created through thermochemical processes deep in a thick, crushing atmosphere. The planet likely has an atmospheric pressure hundreds of times greater than Earth's, with no solid or liquid surface anywhere. You can't land on K2-18b. If you descended through its atmosphere in a spacecraft, you'd just keep sinking deeper into increasingly dense gas until the pressure crushed your vessel. There's no ocean to discover, no surface to explore. It's just gas all the way down to an uncertain core. This discovery was a significant disappointment because K2-18b is located in its star's habitable zone. On paper, it checked many boxes, but being in the habitable zone means nothing if you don't have a surface where liquid water can exist. K2-18b is yet another world that appeared promising but turned out to be uninhabitable. These repeated disappointments are teaching us humility. The universe is under no obligation to be hospitable to life. Planets don't form with the goal of becoming habitable. They form according to the laws of physics, chemistry, and probability. Most of the time, those laws produce dead worlds. We need to talk about magnetic fields because they play a crucial role in planetary habitability that often gets overlooked in popular discussions. Earth has a strong magnetic field generated by the churning motion of molten iron in our planet's outer core. This magnetic field extends far into space, creating a protective bubble called the magnetosphere. The magnetosphere deflects most of the charged particles streaming from the sun in what we call the solar wind. Without this protection, those particles would constantly bombard our upper atmosphere, gradually stripping it away. Mars lost much of its atmosphere this way after its global magnetic field shut down billions of years ago. For a planet to generate a magnetic field through this dynamo mechanism, it needs several things. It needs a molten, electrically conductive layer in its interior, typically iron. It needs sufficient internal heat to keep that layer molten and convecting, and it needs to be rotating fast enough to organize those convection currents into a coherent magnetic field. Smaller planets have a harder time maintaining these conditions. They cool faster because they have more surface area relative to their volume. Once the interior solidifies, the dynamo shuts down and the magnetic field disappears. This is what happened to Mars. It's smaller than Earth, cooled more quickly, its core solidified, and its magnetic field vanished, leaving the planet vulnerable to atmospheric stripping by the solar wind. Tidally locked planets face additional challenges maintaining magnetic fields. The dynamo mechanism that generates magnetic fields depends partly on planetary rotation. Earth rotates once every 24 hours, and this rotation helps organize the convection currents in our outer core. But if a planet is tidally locked, it rotates extremely slowly once per orbit, which might be only a few days or weeks. This slow rotation might make it difficult or impossible to generate a strong magnetic field. Without magnetic protection, even planets with thick atmospheres might gradually lose them to stellar wind erosion. Over billions of years, the constant bombardment strips away gas molecules, thinning the atmosphere until it can no longer support liquid water on the surface. The planet dies slowly, bleeding its atmosphere into space. Some scientists have proposed that planets without global magnetic fields might still be protected if they have strong ionospheres, layers of ionized gas in the upper atmosphere that can partially deflect charged particles. Venus, which lacks a global magnetic field, has such an ionosphere. But Venus also has an incredibly thick atmosphere to begin with, roughly 92 times the pressure of Earth's atmosphere. It can afford to lose gas to space because it has so much to spare. A planet like Mars with a thinner atmosphere doesn't have that luxury. Once the magnetic field disappeared, Mars was doomed to atmospheric loss. The ionosphere couldn't provide enough protection. Today, Mars loses about 100 grams of atmospheric gas to space every second. That might not sound like much, but over billions of years, it adds up to an entire atmosphere worth of material lost to space. Now let's zoom out and think about the bigger picture. What does all this mean for the prevalence of life in the universe? When we add up all these challenges, all the ways planets can fail to maintain habitability, the picture becomes rather bleak. You need a planet of the right size, not too big, and not too small. You need it to form at the right distance from its star in the habitable zone. You need the star to be the right type, not too active and not too massive. You need the planet to avoid runaway greenhouse effects during formation. You need it to acquire and retain water. You need it to generate a protective magnetic field. You need it to avoid catastrophic impacts that strip away its atmosphere. You need it to avoid being disrupted by migrating giant planets. You need its star to remain stable for billions of years. Even if all those conditions are met, you still need life to actually originate, which requires chemical conditions we don't fully understand. Then you need that life to survive for billions of years without being completely sterilized by asteroid impacts, supervolcanic eruptions, or other catastrophes. Then you need complex life to evolve. Then you need intelligence to emerge. Each of these steps is a filter. Each one eliminates a large fraction of planets from consideration. When you multiply all these probabilities together, the number of planets that successfully navigate every challenge becomes very small. This line of thinking relates to something called the Fermi paradox, named after physicist Enrico Fermi. The paradox goes like this: the universe is vast and ancient. Even if intelligent life is rare, there should still be many technological civilizations out there. Some should be millions or billions of years older than us. Where is everybody? Why haven't we detected any signals or evidence of alien civilizations? One possible answer is called the Great Filter. This hypothesis suggests there's some step in the evolution from non-living matter to spacefaring civilization that's incredibly difficult to pass. Most attempts fail. The filter might be the origin of life itself. It might be the jump from single-celled to multicellular organisms. It might be the emergence of intelligence. Or it might be some challenge we haven't yet faced, something that typically destroys civilizations before they can spread to the stars. The discovery that dead worlds might vastly outnumber living ones suggests that one major filter is simply maintaining habitable conditions long enough for complex life to evolve. Most planets fail at this step. They lose their atmospheres, they become tidally locked hellscapes, they boil away in runaway greenhouse effects, they freeze when their stars dim, or they get sterilized by stellar flares. Earth, it seems, is lucky. We orbit a remarkably stable star. We're just the right size to hold on to our atmosphere while avoiding becoming a mini Neptune. We have a strong magnetic field generated by our churning iron core. We have plate tectonics that recycle carbon dioxide and help regulate our climate over geological timescales. We have a large moon that stabilizes our axial tilt, preventing extreme climate swings. We avoided being ejected by migrating giant planets. Every one of these factors could easily have gone differently. If Earth had been 15% smaller, we might have ended up like Mars, losing our atmosphere and water over billions of years. If we'd been 15% larger, we might have captured too much hydrogen and helium during formation, becoming a mini Neptune with no solid surface. If Jupiter had migrated inward instead of staying in the outer solar system, Earth might have been flung into interstellar space or crashed into the Sun. We exist because we won a cosmic lottery. We drew the winning ticket from billions of possibilities, and we're only now beginning to appreciate how rare that winning combination might be. But let's be clear about something important. When we talk about dead worlds, we're using a very specific definition of dead. We mean worlds without life, without the complex chemistry that leads to biology as we understand it. But these worlds aren't worthless. They're not failures. Each one is a natural experiment, a data point helping us understand planetary science. LHS 3844b, with its lava hemisphere and frozen hemisphere, teaches us about tidal locking and atmospheric dynamics. L98-59d, with its permanent magma ocean, reveals how rocky planets interact with intense stellar radiation. K218b shows us that planets in the habitable zone aren't automatically habitable. Every discovery, even the disappointing ones, adds to our knowledge, and there's another perspective worth considering. Even if a planet can't support life, it might still be scientifically fascinating. Some dead worlds might have complex geology, dramatic weather systems in their thin atmospheres, or unique chemical processes we've never observed before. They're laboratories where nature runs experiments we could never conduct on Earth. Imagine standing on the surface of a tidally locked planet, right at the terminator between eternal day and eternal night. Behind you, the sun hangs frozen at the horizon, never rising or setting. In front of you, the stars shine steadily in a black sky. Winds howl past you, carrying heat from the scorching day side to the frozen night side. The ground beneath your feet might be twisted and tortured by tidal forces from the nearby star. It would be hostile to life, but undeniably alien and awe-inspiring. Or imagine descending through the atmosphere of a mini Neptune, sinking through layers of hydrogen and helium, past clouds of exotic chemicals we've never seen on Earth. Deeper and deeper you go, watching the pressure gauge climb. The gas around you becomes denser, transitioning from atmosphere to ocean to something in between. Perhaps you'd eventually reach a core of rock or metal, or perhaps the gas just becomes supercritical fluid all the way down. Either way, it's a world utterly unlike our own. These dead worlds expand our sense of what's possible. They show us the incredible diversity of planetary outcomes. They remind us that Earth-like planets are just one possibility among many, and probably not the most common one. But I'd be lying if I said these discoveries don't also inspire some melancholy. When we look at the night sky, we're looking at hundreds of billions of stars in our galaxy alone. For most of human history, we wondered if planets orbited those stars. Now we know they do. The universe is full of worlds. Yet many or most of those worlds might be barren, silent, empty. Rocks orbiting stars, undergoing geological processes, experiencing weather and volcanism and tectonics, but without anyone to witness them. No eyes to see their strange sunrises, no minds to contemplate their mysteries. There's a philosophical dimension to this realization. We live in a universe that's unimaginably vast, filled with countless worlds, yet most of them might be lifeless. What does that mean for our place in the cosmos? Does it make life more precious, knowing how rare it might be? Or does it make existence seem more absurd, a tiny flicker of complexity in an ocean of dead matter? I think it depends on your perspective. Some people find comfort in rarity. If life is uncommon, then Earth becomes more special, more worthy of protection. Every species, every ecosystem, every human life becomes more valuable because we might be among the only living things in vast stretches of space. Others find it isolating, the idea that we might be alone, or nearly alone, in a galaxy full of dead worlds feels desperately lonely. It's one thing to imagine the universe teeming with life, even if we haven't detected it yet. It's quite another to contemplate being the only voices in an otherwise silent cosmos. But here's something to consider. Even if dead worlds vastly outnumber living ones, vastly outnumber doesn't mean completely dominate. Let me explain with some numbers. Our galaxy contains somewhere between 200 and 400 billion stars. Let's be conservative and say 200 billion. Only 1 in a million stars hosts a planet with life. That's still 200,000 living worlds in our galaxy alone. If only 1 in a billion stars hosts a planet with complex life, that's still 200 planets with ecosystems as rich as Earth's. The universe contains roughly 2 trillion galaxies. If our galaxy has 200 living worlds, and that's typical, then the observable universe contains 400 billion living worlds. That's an enormous number, even if it represents only a tiny fraction of all planets. So even in a universe where dead worlds are the overwhelming norm, life might still be abundant in absolute terms. The distances between living worlds would be vast, the isolation profound, but existence itself wouldn't be rare. We just wouldn't have many neighbors. This is the strange arithmetic of cosmic scale. Even incredibly unlikely events happen countless times when you have enough opportunities. A 1 in a billion chance becomes a certainty when you roll the dice 1 trillion times. The real question isn't whether life exists elsewhere. With numbers this large, it almost certainly does, even if habitable planets are exceptionally rare. The real question is whether intelligent, technological life is common enough for us to ever make contact. If the nearest civilization is 20,000 light-years away, we'll probably never communicate with them. Even at the speed of light, a message would take 20,000 years to reach them, and another 20,000 years for their reply to return. That's longer than human civilization has existed. We'd be shouting into the void, hoping someone hears us millennia from now. But let's return to the science and explore some additional mechanisms that create dead worlds. We've covered a lot of ground, but there are still more ways for planets to fail at habitability. One particularly insidious mechanism is atmospheric collapse. This can happen when a planet's atmosphere becomes cold enough that its constituent gases literally freeze out and fall to the ground as ice or snow. Mars experiences a mild version of this seasonally. During Martian winter at the poles, it gets cold enough for carbon dioxide, the main component of Mars's thin atmosphere, to freeze. Layers of dry ice accumulate at the poles, temporarily removing carbon dioxide from the atmosphere. During summer, the dry ice sublimates back into gas. This seasonal cycle causes Mars's atmospheric pressure to vary by about 25% throughout the year. But imagine a more extreme scenario. A planet farther from its star, in the outer reaches of the habitable zone, might experience a runaway cooling process. Maybe volcanic activity decreases, reducing the amount of greenhouse gases being added to the atmosphere. Without those gases to trap heat, temperatures drop. As temperatures drop, gases begin to freeze out. With less gas in the atmosphere, the greenhouse effect weakens further. Temperatures drop more gas freezes. It's a vicious cycle. Eventually, the planet's entire atmosphere could collapse, leaving nothing but frozen lakes of nitrogen and carbon dioxide on the surface. The planet becomes essentially airless, its atmosphere locked away as ice, unable to protect or warm the surface. This is planetary death by freezing. Scientists think this might have happened to Pluto, though Pluto was never in the habitable zone. But a similar process could affect planets in the outer habitable zone if conditions align badly. Once the atmosphere collapses, it's very difficult for the planet to recover. The frozen gases would need to be vaporized again, which requires either intense internal heating from volcanism or a dramatic increase in stellar radiation. Another threat to habitability comes from the planet's own interior. We've mentioned the importance of geological activity, particularly plate tectonics, for maintaining Earth's climate. But what happens when a planet's interior cools and geological activity ceases? Earth's plate tectonics works because our mantle is hot enough to flow even though it's technically solid rock. The mantle convects with hot material rising and cool material sinking. This convection drives the motion of tectonic plates at the surface. Plates collide, forming mountains. They spread apart, creating new ocean floor. They slide past each other, generating earthquakes. This constant recycling serves a crucial purpose beyond just creating dramatic landscapes. When rain falls on continents, it weathers rocks, creating chemical reactions that pull carbon dioxide out of the atmosphere and wash it into the ocean as dissolved carbonates. Sea creatures use these carbonates to build shells. When they die, their shells sink to the ocean floor, trapping carbon. Over millions of years, this process buries enormous amounts of carbon on the seafloor. If it continued unchecked, it would eventually remove all the carbon dioxide from the atmosphere. Without carbon dioxide, Earth's greenhouse effect would weaken, temperatures would plummet, the planet would freeze. But plate tectonics prevents this. Seafloor spreading carries those carbon-rich sediments into subduction zones, where one tectonic plate slides beneath another. The descending plate gets dragged deep into the mantle, where intense heat and pressure cook the carbonate sediments, releasing carbon dioxide. This carbon dioxide then escapes back to the atmosphere through volcanic eruptions. It's a beautifully balanced cycle. Weathering removes carbon dioxide from the atmosphere. Volcanism returns it. The system self-regulates over millions of years, helping to keep Earth's climate stable enough for life to thrive. Now imagine a planet without plate tectonics. Perhaps it's slightly smaller than Earth, so its interior cooled faster. Perhaps it never developed the specific conditions necessary for plate tectonics to begin. Whatever the reason, its surface is a single, solid shell. No plates, no subduction, no recycling. On such a planet, carbon dioxide would still get pulled out of the atmosphere by weathering, but it wouldn't get recycled back through volcanism. Over tens or hundreds of millions of years, the atmosphere would gradually lose carbon dioxide. The greenhouse effect would weaken, temperatures would drop. Eventually, the planet would become too cold for liquid water. Life, if it had ever existed, would go extinct. Venus might be an example of a planet that lost plate tectonics, though its story is more complicated. Venus has no evidence of current plate tectonic activity. Its surface is a solid shell. But it has clearly experienced massive volcanic episodes in its past, resurfacing much of the planet roughly 500 million years ago. Some scientists think Venus might have had plate tectonics early in its history, but lost it at some point. Without plate tectonics to recycle carbon dioxide, volcanic outgassing from the planet's interior built up enormous amounts of CO2 in the atmosphere with no mechanism to remove it. This led to the runaway greenhouse effect that turned Venus into the hellscape we see today. So the absence of plate tectonics can kill a planet either by freezing it through carbon dioxide depletion or by overheating it through carbon dioxide accumulation, depending on how much volcanic activity continues. Either way, the planet loses the climate regulation that plate tectonics provides. Earth is the only planet in our solar system with active plate tectonics. We don't know how common this process is throughout the universe. It might be relatively rare, requiring a specific combination of planetary size, composition, water content, and thermal history. If that's true, then many rocky planets might lack this crucial climate regulation mechanism, making long-term habitability much more difficult. Let's talk about another category of dead worlds, planets that had everything going for them but got unlucky with asteroid impacts. We've discussed this briefly, but it deserves deeper exploration because the impact history of a planet can completely determine its fate. Early in any solar system's history, there's an enormous amount of debris left over from planet formation. Asteroids, comets, and planetesimals fill the space between planets. These objects frequently collide with planets in what we call the late heavy bombardment period. For Earth, this occurred roughly 4 billion years ago. During this chaotic era, Earth was pummeled by countless impacts. Some were small, creating craters that have long since eroded away. Others were absolutely massive, delivering enough energy to vaporize oceans and sterilize the surface. If life had originated during this period, it might have been wiped out and had to start over multiple times. But Earth survived because the late, heavy bombardment eventually ended. Most of the debris got swept up by planets or ejected from the solar system through gravitational interactions with Jupiter. The impact rate declined dramatically. Life got a chance to establish itself without constantly being reset to zero. Not all planetary systems might be so fortunate. If a solar system has a particular configuration of giant planets, gravitational dynamics might keep the asteroid belt stirred up, maintaining a high impact rate for much longer. Planets in such systems would get bombarded continuously, perhaps for billions of years instead of just a few 100 million. Imagine trying to establish life on a planet that experiences a major extinction-level impact every 10 million years. Life might start, but before it could evolve much complexity, another impact would sterilize the surface. Only organisms deep underground or in deep ocean vents might survive, and they'd have to recolonize the surface after each catastrophe. Complex life requires stability over long timescales. On Earth, it took roughly 3 billion years for multicellular organisms to evolve after life first appeared. 3 billion years of relative stability without any impacts severe enough to completely sterilize the planet. If Earth had experienced even one truly massive impact during that time, something large enough to vaporize the oceans completely, life might have been reset to its earliest stages and we wouldn't be here today. So some potentially habitable planets might remain perpetually stuck with only simple life or no life at all, simply because they're unlucky enough to orbit in solar systems with particularly chaotic impact environments. There's also the question of late impacts, ones that occur after complex life has evolved. The dinosaur extinction 66 million years ago was caused by an asteroid only about 10 kilometers in diameter. That's tiny by cosmic standards, yet it was enough to trigger a mass extinction that eliminated 3/4 of all species. Now imagine an impact 10 times larger or 100 times larger. An asteroid 100 kilometers across would release energy equivalent to roughly 100 million megatons of TNT. The impact would create a crater hundreds of kilometers wide. It would throw so much debris into the atmosphere that the planet would be shrouded in darkness for years. Photosynthesis would cease. Food chains would collapse. Surface temperatures would plunge. Such an impact might not completely sterilize a planet, but it would set back the evolution of complex life by hundreds of millions of years. And if such impacts occurred relatively frequently, once every few 100 million years, complex life might never get a chance to develop intelligence and technology. Earth has been extraordinarily lucky in this regard. We've experienced major impacts, yes, but they've been spaced far enough apart that life has had time to recover and continue evolving. The dinosaur extinction, catastrophic as it was, actually opened up ecological niches that allowed mammals to diversify and eventually led to humans. The impact was destructive, but it didn't permanently end the story of complex life on Earth. Many planets might not be so fortunate. They might experience frequent severe impacts that keep resetting the evolutionary clock. These would be living worlds in the sense that they host simple life, but they'd be effectively dead from the perspective of complex ecosystems and intelligent beings. Let me now address another fascinating and sobering reality. The chemical composition of a planet's atmosphere can make it uninhabitable even if all other conditions seem right. We tend to think of breathable atmospheres as the norm for habitable planets, but that's only because we evolved in Earth's current atmospheric composition. Our atmosphere is roughly 78% nitrogen, 21% oxygen, and trace amounts of other gases. The oxygen is almost entirely a product of biological activity, specifically photosynthesis by plants and cyanobacteria. Early Earth had essentially no free oxygen in the atmosphere. For the first 2 billion years of life's existence on Earth, organisms were anaerobic, meaning they didn't use oxygen for respiration. Then, around 2.4 billion years ago, cyanobacteria evolved photosynthesis and began pumping oxygen into the atmosphere. This actually caused a mass extinction event called the Great Oxidation Event. Oxygen is highly reactive and was toxic to most organisms alive at the time. The rise of oxygen killed off huge portions of the anaerobic biosphere. But it also opened up new possibilities. Oxygen-breathing organisms can extract far more energy from food than anaerobic ones, enabling the evolution of complex, energy-hungry, multicellular life. Now imagine a planet where photosynthesis never evolved, or evolved but produced a different waste gas. The planet might be teeming with microbial life, warm and wet and seemingly habitable, but with an atmosphere that would be deadly to us. Perhaps the atmosphere is dominated by methane and hydrogen sulfide, both produced by anaerobic organisms. Perhaps there's very little oxygen at all. Such a planet would appear alive if we could detect biosignature gases in its atmosphere, but it would be completely incompatible with any life form that requires oxygen. It would be alive but alien in the most fundamental sense. Conversely, a planet might have an oxygen-rich atmosphere through non-biological means. Photodissociation of water vapor by stellar ultraviolet radiation can produce oxygen. If the hydrogen escapes to space and the oxygen accumulates, you could end up with a significant amount of oxygen in the atmosphere, even without life. This creates a potential false positive in our search for life. If we detect oxygen in an exoplanet's atmosphere, our first instinct might be to assume it's a biosignature. But it could also be a sign of a dead world that lost its water to photodissociation. Distinguishing between these scenarios requires careful analysis of other atmospheric components and the planet's overall environment. Some planets might have atmospheres that are corrosive or toxic in ways we haven't even considered. Super-Earths with thick atmospheres might develop high-pressure chemical reactions that produce gases that would dissolve flesh or corrode metal on contact. Mini-Neptunes might have upper atmospheres filled with complex organic hazes, similar to Saturn's moon Titan, but without the solid surface that makes Titan interesting. The point is that having an atmosphere isn't enough. The composition matters enormously, and the range of possible atmospheric compositions is vast, with only a tiny subset being compatible with life as we know it, and an even tinier subset being compatible with complex, intelligent life. Speaking of atmospheric composition, let's discuss the problem of hydrogen escape in more detail, because it's a major factor in planetary habitability that often gets overlooked. Hydrogen is the lightest element. It has a very low molecular weight, which means hydrogen molecules move faster at any given temperature than heavier molecules. If they move fast enough to exceed the planet's escape velocity, they'll leave the atmosphere and drift into space. This process, called Jeans escape, happens continuously on every planet, but at different rates depending on the planet's mass and temperature. Earth loses hydrogen this way, but slowly enough that it doesn't significantly affect our atmosphere over billions of years. We don't have much free hydrogen anyway, since it combines with oxygen to form water. But for smaller planets or planets closer to their stars, which are hotter, hydrogen escape can be rapid. If a planet acquired a hydrogen-rich atmosphere during formation, it might lose that atmosphere entirely over just a few 100 million years. This is particularly relevant for mini-Neptunes and sub-Neptunes. These planets have thick hydrogen-helium envelopes. If they orbit too close to their stars, stellar radiation heats the upper atmosphere, accelerating hydrogen escape. The planet essentially boils off its atmosphere into space. Astronomers have observed this process happening on several exoplanets. They've detected huge cometary tails of hydrogen streaming away from hot Neptunes, planets losing their atmospheres in real time. Over millions or billions of years, these planets might lose so much of their hydrogen envelopes that they shrink down to just their rocky cores, becoming super-Earths. Oh, this sounds promising, right? Maybe mini-Neptunes can become habitable by losing their thick atmospheres. Unfortunately, it's not that simple. The process of losing a hydrogen envelope is violent and involves extreme radiation exposure. By the time the planet finishes shedding its hydrogen, it's likely been baked sterile by stellar radiation. Any water that might have been present has probably been lost as well. Moreover, the leftover rocky core might not resemble Earth at all. It could be composed of different materials with different properties. It might lack the right mix of elements to support life. It might have no magnetic field, leaving it vulnerable to continued atmospheric stripping by stellar wind. These stripped mini-Neptunes are probably just another category of dead world, barren rocks that once had thick atmospheres but lost them through violent processes. Now let's consider a particularly exotic category of dead worlds, rogue planets, worlds that don't orbit any star at all. These are planets that formed in orbit around a star but were gravitationally ejected from their solar systems during chaotic early periods when planetary orbits were still settling. Computer simulations of planetary system formation suggest that rogue planets might actually be extremely common. For every planet that remains in orbit around its star, there might be one or more that got ejected into interstellar space. Our galaxy could contain billions of these lonely wanderers drifting through the darkness between stars. Rogue planets are almost certainly dead by our definition. Without a star to warm them, they're frozen wastelands. Any atmosphere they had when they were ejected would gradually freeze and fall to the surface as snow. The surface temperature would be just a few degrees above absolute zero, kept barely above total freezing only by residual heat from radioactive decay in the planet's interior. And yet there's a remote possibility that some rogue planets might harbor life. If a planet is large enough and has enough radioactive elements in its interior, heat from radioactive decay could keep the subsurface warm enough for liquid water to exist beneath a thick layer of ice. This is similar to how Jupiter's moon Europa and Saturn's moon Enceladus maintain subsurface oceans beneath ice shells. A rogue planet with a subsurface ocean would be pitch black, isolated from any external energy source, but it might still host microbial life around hydrothermal vents on the ocean floor. These ecosystems would be based entirely on chemical energy from the planet's interior, just like the deep-sea vent communities on Earth that exist in total darkness. Detecting life on a rogue planet would be essentially impossible with current technology. These planets emit no light of their own except faint infrared radiation from their residual heat. They're incredibly difficult to spot even with our best telescopes. We've only discovered a handful of potential rogue planets so far, and confirming their nature is challenging. But the idea that our galaxy might contain countless frozen worlds drifting through the void, some possibly harboring hidden oceans beneath miles of ice, is simultaneously haunting and wondrous. It expands our conception of where life might exist. It suggests that even the darkest, most isolated corners of the galaxy might not be completely dead. Still, even if some rogue planets have subsurface life, they'd remain profoundly isolated. No sunlight reaches them, no energy arrives from any external source. Any life that evolved there would be trapped in eternal darkness, with no possibility of developing technology or intelligence. The energy available from hydrothermal vents alone isn't enough to support complex ecosystems, so while rogue planets might not be completely dead, they're functionally equivalent to dead worlds from the perspective of the broader cosmic story of life. Let's shift focus to one more mechanism that creates dead worlds: stellar evolution beyond the main sequence. We discussed earlier how stars like the Sun gradually brighten over billions of years, eventually making their planets uninhabitable. But the final stages of stellar evolution are even more dramatic. When the Sun exhausts the hydrogen fuel in its core, about 5 billion years from now, it will begin fusing hydrogen in a shell around the core. This will cause the star to expand dramatically, becoming what astronomers call a red giant. The Sun will swell to perhaps 100 times its current diameter, possibly engulfing Mercury, Venus, and maybe even Earth. Planets that survive this expansion won't emerge unscathed. The Sun's outer layers will be diffuse and tenuous during its red giant phase, but they'll still exert drag on any planets orbiting within them. This drag will cause planets to spiral inward, eventually falling into the Sun's core. Even planets that orbit far enough out to avoid being engulfed will be scorched by the enormously increased radiation from the bloated red giant. Jupiter's icy moons might briefly experience liquid water on their surfaces as they're heated by the red giant Sun, but this habitable phase would last only a few million years before the Sun sheds its outer layers in a planetary nebula, leaving behind a white dwarf remnant. A white dwarf is the dense, hot core of a dead star, roughly the size of Earth but with about half the Sun's mass. It doesn't undergo fusion, it just slowly cools over billions of years, radiating away its residual heat. Any planets that survive the red giant phase would find themselves orbiting a fading ember, receiving less and less warmth until they freeze completely. We've actually discovered planets orbiting white dwarfs, identified by watching them transit in front of their tiny host stars. These planets are certainly dead now, frozen remnants from a bygone era when their star still burned. They're monuments to solar systems that once were, silent witnesses to stellar death. Some scientists have speculated that planets in the right orbits around white dwarfs might be habitable during the white dwarf's early cooling phase, when it's still hot enough to warm nearby planets. The habitable zone around a white dwarf would be very close, much closer than Mercury orbits the Sun, but a planet in that zone might receive enough heat for liquid water. The problem is getting a planet into that orbit. Planets that were originally close enough would have been destroyed during the red giant phase. Only planets that originally orbited farther out and then migrated inward after the star became a white dwarf could occupy the habitable zone. And the migration process itself would likely be violent and destructive. Moreover, white dwarfs cool relatively quickly. A habitable zone around a white dwarf might only remain habitable for a few 100 million years before the star cools too much. That's probably not enough time for complex life to evolve from scratch, though simple life might persist if it somehow survived the transition from the star's main sequence phase to the white dwarf phase. So planets around white dwarfs are almost certainly dead worlds. They might be geologically interesting, composed of exotic materials forged during their star's final death throes, but they're not homes for life. Massive stars have an even more violent end. Stars, significantly more massive than the Sun, burn through their fuel much faster. A star 20 times the mass of the Sun might live only 10 million years before exhausting its nuclear fuel and exploding as a supernova. This explosion releases more energy in a few seconds than the star emitted during its entire lifetime. Any planets in the system would be vaporized, blown apart by the shock wave, or irradiated to sterility by the intense burst of high-energy photons and cosmic rays. Nothing survives a supernova at close range. The supernova leaves behind either a neutron star or a black hole, depending on the mass of the progenitor star. Either way, any planets that might have somehow survived the explosion would find themselves in an utterly hostile environment. Neutron stars have incredibly strong magnetic fields and emit intense beams of radiation. Black holes obviously can't support planetary habitability in any conventional sense. We have discovered planets orbiting neutron stars, detected through precise timing of the neutron star's radio pulses. These pulsar planets are thought to be second-generation worlds, formed from the debris of the supernova itself. They're certainly dead, bombarded constantly by radiation from the neutron star, but they're fascinating objects that reveal how planetary systems can form even in the most extreme environments. All of this stellar evolution means that habitability has a finite window. For planets around Sun-like stars, that window is perhaps 10 billion years, from when the star settles onto the main sequence until it expands into a red giant. For planets around more massive stars, the window might be just a few million years. For planets around red dwarfs, the window could be 100 billion years or more, but those planets face other challenges we've discussed. Every planetary system has an expiration date. Every habitable world will eventually become uninhabitable as its star evolves. The universe doesn't preserve habitability indefinitely. Dead worlds are the ultimate fate of all worlds. This brings us to one of the most philosophically challenging aspects of the dead world problem, the question of whether we should care about all these lifeless planets. Does it matter that most worlds are barren? Does it diminish the universe somehow? I think the answer depends on what we value. If we value life and consciousness as the highest goods, then yes, a universe full of dead worlds seems like a terrible waste. All that matter, all that complexity, all those countless worlds, and almost none of them giving rise to anything that can appreciate the cosmic story. But if we value diversity and natural processes for their own sake, then dead worlds aren't failures. They're examples of the incredible range of outcomes that physics and chemistry can produce. Each dead world is a unique experiment in planetary science, teaching us something about how matter organizes itself under different conditions. There's also a pragmatic perspective. Understanding dead worlds helps us protect Earth. Every mechanism that creates a dead world is a cautionary tale for our own planet. Runaway greenhouse effects, magnetic field collapse, atmospheric loss, impact catastrophes. These aren't just abstract dangers facing distant exoplanets. They're potential futures for Earth if we're not careful. Climate change, for instance, is often discussed in terms of economic costs and political challenges. But the deeper truth is that we're conducting an experiment with our atmosphere that mirrors the processes that killed Venus. We're pumping greenhouse gases into the air, warming the planet, and hoping we can stop before triggering irreversible feedback loops. Venus shows us what happens when those feedbacks run to completion. It's a warning written in another world's atmosphere, a cautionary tale we should heed. The same goes for Mars and magnetic field loss, or the tidally locked exoplanets and atmospheric dynamics. Each dead world teaches us something about planetary fragility. In that sense, studying dead worlds isn't morbid fascination. It's essential homework for a species that wants to survive in the long term. We need to understand how planets die so we can prevent Earth from following that path. There's also the practical consideration of space colonization. If humanity ever ventures beyond Earth to settle other worlds, we'll need to understand what makes planets habitable and how to recognize the warning signs of environmental collapse. The lessons we learn from dead worlds will be directly applicable to assessing potential colony sites. Mars, for example, is often proposed as a target for colonization, but Mars is a dead world. It has no magnetic field, almost no atmosphere, surface temperatures that average -63 degrees Celsius, and no liquid water. Colonizing Mars would require enormous technological efforts to overcome these challenges, essentially terraforming the planet or building enclosed habitats. Understanding why Mars died, the loss of its magnetic field, the subsequent atmospheric stripping, the cooling of its interior, helps us evaluate whether Mars could ever be truly habitable again, or whether human presence there would always require life support systems. The same applies to other potential colony sites. The Moon is airless and dead. Venus is a hellscape. The outer planets are gas giants with no solid surfaces. Their moons might offer possibilities: Europa, with its subsurface ocean, Titan with its thick atmosphere, and liquid methane lakes. But these are still profoundly alien environments, nothing like Earth. If we want to find new homes among the stars, we need to find living worlds, or at least worlds that could be made living with reasonable effort. Understanding dead worlds helps us narrow the search, identifying which planets are beyond redemption and which might have potential. Some scientists dream of terraforming, the process of deliberately modifying a planet's environment to make it Earth-like. Mars is the usual target for such proposals. The idea is to thicken Mars's atmosphere by releasing frozen carbon dioxide from the polar caps and subsurface reservoirs, creating a greenhouse effect that warms the planet enough for liquid water to exist on the surface. But recent studies suggest there isn't enough accessible carbon dioxide on Mars to create a thick atmosphere through terraforming. Most of Mars's carbon dioxide was lost to space billions of years ago. What remains is locked in minerals or frozen in places we can't easily access. Terraforming Mars might be impossible with foreseeable technology. This is another lesson from dead worlds. Death might be permanent. Once a planet loses its atmosphere to space, once its magnetic field shuts down, once its interior cools and geological activity ceases, reversing those processes might be beyond our capabilities. Dead worlds might stay dead, no matter how desperately we want to revive them. That makes Earth even more precious. We live on a rare gem, a planet that won the cosmic lottery and maintained habitability for billions of years. We evolved here, adapted to these specific conditions, dependent on this particular atmosphere and climate and biosphere. There might not be another Earth within reach, and if we destroy this one, we might not get a second chance. So let's circle back to where we began, the question of how common dead worlds really are. Based on everything we've discussed, the challenges of planetary formation, the dangers of tidal locking, the problems with mini-Neptunes, the threats from stellar activity, the difficulty of maintaining atmospheres and magnetic fields, the risks of runaway greenhouse and snowball effects, the perils of asteroid impacts, the requirements for plate tectonics and climate regulation, the constraints of atmospheric composition, and the inevitability of stellar evolution, it seems clear that habitable planets are rare. Most worlds are dead. That's the reality the data is showing us. It's not what we hoped to find when we started discovering exoplanets, but it's what the universe has revealed. Most planets are too hot or too cold, too big or too small, too close to their stars or too far away, tidally locked or bombarded by radiation, airless or smothered in hydrogen, geologically dead, or volcanically hyperactive. The universe is a harsh place for life. The conditions required for habitability are stringent. The windows of opportunity are narrow, the threats are numerous. Most worlds never had a chance, and many that did failed somewhere along the way. But here's the counterpoint, the reason for hope. Despite all this bleakness, we exist, Earth exists, life exists. Against all odds, against all the mechanisms that create dead worlds, this planet succeeded. We're here, alive, conscious, contemplating our place in the universe. That means it's possible. Rare, yes. Difficult, absolutely. But possible. And if it happened once, it can happen again. Somewhere out there among the hundreds of billions of stars in our galaxy, there are probably other living worlds. Maybe not many, maybe only a handful in the entire galaxy, but they're out there. And that makes our existence and the existence of any other living world extraordinarily precious. We're not just alive, we're improbably, almost miraculously alive. With the universe becoming aware of itself, matter organized into patterns complex enough to contemplate its own existence. Every living world is a beacon in the darkness, a brief candle flame in an ocean of cold, dead matter. We should cherish that, we should protect it, we should do everything in our power to make sure Earth doesn't join the legions of dead worlds we're discovering, because make no mistake, Earth could die. All the mechanisms we've discussed, atmospheric loss, climate collapse, magnetic field failure, impact catastrophes, could happen here. Not tomorrow, not next year, but over geological timescales, Earth faces all the same threats that killed other worlds. Our planet is only temporarily alive, borrowing time from an indifferent universe. The question is whether we'll use that borrowed time wisely. Will we be good stewards of the rare, precious thing we've inherited? Will we learn from the dead worlds around us and avoid their fates? Or will we squander Earth's habitability through negligence, greed, or ignorance, adding one more dead world to the universe's vast collection? I don't know the answer. Nobody does. We're writing that story right now, collectively, through billions of individual choices and actions. But I hope we choose wisely. I hope we recognize how special Earth is, how unlikely our existence, how fortunate we are to live on a world that hasn't died, because out there, orbiting distant stars, are countless dead worlds, silent, frozen or scorched, airless or smothered, barren or toxic. They had their chances and failed, or never had chances at all. They're monuments to entropy, to the universe's general tendency toward disorder and death. Earth doesn't have to join them, not yet, not if we're careful. Not if we learn from their stories and write a different ending for our own. The universe is mostly dead. But here, on this improbable blue marble, life flourishes. Let's keep it that way. Speaking of planetary challenges, if you're intrigued by the hurdles of making dead worlds habitable, check the video on the screen. The terrifying problem with colonizing Mars, it'll completely change how you think about humanity's future in space. See you there.